All right, so we're moving on from Leibnizian modal logic to Meinongian free logic, and this is a lecture on the semantics of Meinongian free logic. So in English, the sentence "something exists" is a little strange, but it's perfectly meaningful. However, it is not a straightforward thing to say in predicate logic. You'll recall that in predicate logic, existence is not a predicate, but an operator. So in other words, in predicate logic, you would not translate Peter exists as capital E, little p. Rather, you would use the identity symbol and write there exists an X, such that X is identical to P. So arguments about whether existence can be treated as a predicate go back hundreds of years. This is partly because a very famous proof of God's existence depends on the assumption that existence is a predicate or a property. This argument is called the ontological argument and was most famously formulated by a philosopher now known as Saint Anselm. Anselm's proof depends on a premise that claims that something that exists is greater, more perfect, than something that doesn't. And he would say that we routinely conceive and speak of non-existent things. Even though I don't own a house in Malibu, I can conceive of a world in which I do. So Anselm also asserts that while this house on the beach I'm imagining is nice, it would be so much nicer if it actually existed. In the ontological argument, he claims that we can all conceive of a supreme being. He calls it a being greater than which cannot be conceived, which you could abbreviate to the greatest conceivable being. But he then asks us to assume that such a being does not exist, the method of indirect proof, and goes on to prove that since something that exists is greater than something that doesn't, this implies a contradiction. So it's easy to follow this argument, but it's also really weird. One obvious thing to suggest is that existence isn't really a predicate or a property. For example, I can imagine a crappy house and just start improving it in my imagination, painting it, renovating it, expanding, putting it on a cliff overlooking the ocean, just all in my mind. But making it exist just doesn't really seem to be an improvement in the same sense. This is what philosophers often claim to be a category mistake, such as if one were to say that some numbers taste better than others. Predicate logic, then, was developed partly to block this sort of thinking about existence. The ontological argument can't be formulated in predicate logic because existence is not a property, but an operator. Now, I actually ought to say that I'm overstating this quite a bit. There isn't anything in the formation rules of predicate logic that prevents you from characterizing existence as a predicate. It's just that it provides you a way of not doing that. So if you insisted on characterizing existence as a predicate by using capital E, you wouldn't be violating any of the rules of predicate logic. So this, of course, should remind you of what we said about the ability to prove God's existence in Leibnizian modal logic. Other logics have been developed that don't permit this. So, by the way, you might assume that people who respond this way to proofs of God's existence must be dogmatic atheists. Some are, but it's not necessarily the case. One may believe in God, but also believe that this argument in favor of God's existence is just problematic. This is typical of a philosophical mindset. We're less interested in the conclusions than the means by which these conclusions are derived. It's very common in philosophy for people who actually agree that something is true to object very strongly to a particular argument in favor of its truth. Many philosophers that we call empiricists argue more generally that whether or not something exists can't be established by logic alone, but must rest on observation, and that this goes for God as much as for houses and for Sasquatch. Given what we just observed concerning predicate logic blocking the ontological argument, or at least providing us the resources to avoid it, as well as empiricism's take on the nature of existence, you'd naturally assume that the predicate logic translation of Peter exists, remember that's there exists in X such that X equals P, would render this as the contingent truth it appears to be. After all, surely it is not a necessary truth that Peter exists. He exists now, but he didn't used to, and someday he won't again. Well, that's not the case. If you just run, for example, a tree to determine whether or not this is a tautology, negate it. It's not the case that there exists an X such that X equals P. Apply quantifier negation rule. I should check that when I do it. So for all X, it's not the case that X equals P. And then just instantiate to P, which you're required to do. You've got it's not the case that P equals P, which according to the tree rules for predicate logic allows us to close it because that's considered to be contradictory. So it turns out it's a necessary truth because negating it and running a tree produces a contradiction at the end of the one and only one path. So, of course, we could also derive this as a theorem. And because we can do that in Leibnizian modal logic, we could simply, when we're doing derivations, we could simply assert this as a necessity by the N rule. So, as John Knowlton notes, there's nothing mysterious about why this turns out to be the case in predicate logic. The reason is simply that in the semantics of predicate logic, we define models in such a way that every name we use necessarily refers to something in the model. So even in basic predicate logic, if we use a name that doesn't occur in the model, we end up with a formula that's a woof, but which doesn't have a truth value. This isn't how English works, though. In English, as we noted, we use non-referring fictional names all the time. We all know who Lord Voldemort is, and we all know that he does not exist, except in a story. So this problem is not solved by Leibnizian modal logic because Leibnizian modal logic is just an extension of classical predicate logic. Leibnizian modal logic actually creates an inconsistency between the semantics and the proof apparatus because it countenances worlds in which it is false that there is someone identical to Peter. So that means there exists an x such that x equals p in world 1 might be false, even though it is a necessary truth in predicate calculus, and because it is also a theorem, can be introduced as a necessity in the proof system. So in fact, as Nolte points out in the textbook, this problem arises even when names aren't in play. We began thinking about the proposition, something exists. Well, that is something we would express as there exists an x such that x equals x. Doesn't seem like it should be a logical truth either, but if you run a tree on it, you'll see that it absolutely is. So now's a good time to stop and review a few concepts for modal logic. The letter, the cursive V we've been using, does a lot of work in our nomenclature. You'll remember we first used it to refer to an entire Leibnizian model. But we also used it to indicate how different entities are evaluated within the model. When we apply V to a name, as in the value of B, we're talking about the object to which the name refers. So if we're talking about a universe that only contains pecans, then the value of B will be some particular pecan. Remember that in modal logic, names refer to the same entity across worlds. We wouldn't typically write the value of B at world 1 because B refers to the same thing in every world where it exists at all. You might remember this is referred to as the doctrine of trans-world identity. So when we apply V to a predicate, as in the value of G at W1, the value of green in world 1, for example, we're picking out a set of objects. Intuitively, we're picking out the set of objects that have this particular property. This expression is relativized to worlds because different objects can have different properties in different worlds. We can also speak meaningfully of the value of G proper, what we call a complete valuation of G. This will be the set consisting of all the sets of green objects from all the different worlds in V. So the value of a name, which is always a single object, or a predicate, which is a set of objects, which may contain 0 or more objects, is what we call its extension. Think of the name or predicate as extending into the world to select an object or set of objects. V can also be applied to propositions, since propositions may be true in one world and false in another. These two are relative to worlds. The value of a proposition is always a truth value. So if capital G little b means Bianca is green, and the object denoted by Bianca is green in world 1 but not in world 2, then we would write the value of GB at world 1 is 2, and the value of GB at world 2 is false. Finally, since names refer to objects and predicates refer to sets of those objects, we can speak meaningfully of the value of a name belonging to the value of a predicate. So if it is indeed correct to assert that the value of GB at world 1 equals true, then we can assert, also using the membership sign, epsilon, correctly assert that the value of B is an element or member of the value of G at world 1. The value of B, remember, is just the object to which B refers, and the value of G is a set of those objects, so we're just saying B is in that set. Free logic, then, is a non-classical, that is to say deviant, logic that is free of the assumption that every name necessarily refers to something that exists in the model. A relevant valuation rule in classical predicate logic tells us that if P is a one-place predicate and A is a name, then PA is true if and only if the value of A is an element or member of the value of P. So if PA means Alvin is poor, this rule tells us that Alvin is poor is true if and only if there's an object, Alvin himself, that has the property of being poor, if and only if that object exists. There's a corresponding rule telling us that such a statement is false if and only if the object exists and does not have this property. Either way, the object has to exist, that's the point. Remember, in predicate logic, the existence of an object is relative to the model itself. There are no different worlds as in modal logic. If it doesn't exist, then PA doesn't have any truth value at all. So if we want statements referring to non-existent objects to be meaningful, which as you know they are in English, we need to make some kind of alteration to the valuation rules. So as Nolte explains, one approach would just be to adopt a rule that makes all such non-referring, as to say non-denoting statements, false. You could do that. This would be in the spirit of Bertrand Russell's theory of definite descriptions. Bertrand Russell was a very famous early 20th century British philosopher, which holds that a proposition like Jimmy's brother is a genius is false when Jimmy lacks a brother. Another philosopher, British philosopher named P.F. Strawson, who disagreed with this, said this isn't right. He claimed that such propositions are neither true nor false, because the definite description, which functions as a name, just fails to denote. Yet another philosopher named Alexander Meinong argued, contra Strawson, that these statements are perfectly meaningful, but contra Russell, not always false by virtue of being non-denoting. So Meinong argued that we need to acknowledge a realm of non-existent objects. You might reasonably think this is a highly revisionist proposal that would require us to rethink the idea that existence is not a predicate but a quantifier. This turns out not to be the case. Meinongian semantics permits a proposition of the form PA to be true even when A fails to denote. So, in other words, when the object normally denoted by A does not exist. So it restricts, though, the use of existential and universal quantifiers to the domain of existing things. So, for example, for all x f of x in Meinongian free logic, we won't be permitted to infer fc unless c is a member of the domain of existing objects. So, even though we acknowledge a realm containing objects that do not exist, we would have no way of saying in the language itself something contradictory like there exists an object that does not exist. John Nolte notes that Meinong himself, when he was waxing philosophical, preferred to say this realm of non-existing objects well, it contains objects that, while non-existent, still have being. Meinong also said that non-existent objects subsist. Metaphysicians worry about the nature of being, but a logician can basically assume that all Meinong means is that we can say true and false things about these objects, even though they don't exist. Since we've recently learned some modal logic, it's tempting to suppose that when we acknowledge non-existing objects, we're just talking about objects that don't exist in our world, but do exist in other possible worlds. But this isn't correct. In Meinongian semantics, every model has an inner domain and an outer domain. The inner domain is relative to a world and contains only objects existing in that world. The outer domain is not world relative and contains any object at all that can be named. In other words, it includes both existing and non-existing objects. One reason why non-existent objects can't be understood simply as objects that don't exist in the actual world, but do exist in other possible worlds, is that we want to allow for objects that do not exist in any possible world. For example, Oliver Twist is a fictional entity. He is a boy in a novel by Charles Dickens, and he does not exist in this world. But arguably, at least, he does not exist in any possible world either, because he is, by definition, a creature of Charles Dickens' imagination. That said, Meinongian logic is a form of modal logic. The reason is that the inner domain is essentially world relative, and so we must make reference to possible worlds in order to do Meinongian semantics. For example, a statement like, there exists an x such that x is identical to b, will be true in one world and not in another. It will be true only in worlds where the object denoted by b is a member of the inner domain of that world. Beyond being a form of modal logic, Meinongian logic is also a way of extending modal logic to be able to say things that can't be said in classical modal predicate logic. So recall that in classical modal logic, we speak of a multiplicity of possible worlds, and that for any world, W, we speak of its domain, dW, the domain of that world, which is the set of objects in that world. So what's interesting is that we are only able to speak of woofs as being true or false of propositions denoting objects in a particular world. We say, for example, that if P is a one-place predicate and A is a name, whose extension, the value of A, is a member of dW, then the value of PA at W is true if and only if the value of A is an element of the value of P at W, something that we've already reviewed in this lecture. In other words, the semantics of classical modal logic, like the semantics of straight predicate logic, does not allow for a sentence like Oliver Twist is an urchin to be true or false. This is because Oliver Twist does not denote an object in the domain of any world. As Nold explains, this has more to do with the way we think of predicates in modal logic than the way we think of names. Names, after all, can have values, thus they denote objects, in one world and not in another. In classical modal logic, the limiting factor is that the extensions of predicates are relative to the domain of a world. The extension or value of a predicate, the value of P, is necessarily a set of objects. one set from each world consisting of the objects that are P, where each object must exist, i.e. must be in some dW, the domain of some world W. Meinongian semantics, then, is an adjustment to the way we treat predicates in classical modal logic, one that permits us to make meaningful statements in one world about objects that do not exist in that world, or indeed in any world. So, as we already noted, Meinongian semantics distinguishes between an inner and an outer domain of any world. The inner domain is what is just called the domain dW in classical modal logic, the set of objects that exists in W. In Meinongian semantics, we retain the expression dW to refer to the inner domain. The outer domain consists of all of the objects of dW, as well as objects that do not exist in dW. dW is therefore a subset of the outer domain, which we call script O for outer. So in the simplest configuration, we have the big blue sphere, which represents the outer domain, and the smaller white sphere, which represents dW, the inner domain. And dW would actually be a set of possible worlds, which belong to dW, but also belong to the outer domain. So in Meinongian semantics, the predicates now get defined with respect to O, the outer domain, rather than dW. As a result, the extensions of predicates are no longer defined as sets of actual objects belonging to the domain dW of some world, but for all nameable objects, whether they exist or not. And as we noted above, since quantifiers only apply to the inner domain, the valuation rules for quantifiers are unchanged. So really we have a picture that looks more like this, and what we're really trying to capture here is something like we might have an object, say A, that's, say, green in world 1, and say that object A might also be green in world 5. Now, by virtue of belonging to world 1 and world 5, A also belongs to the outer domain. But there also might be some object B that exists only in the outer domain, that doesn't belong to world 1, world 2, world 3, world 4, world 5. Oops, I've got a 2 world 5s there. That should be world 6. Doesn't belong to any of these worlds. And so if we depict it in this way, B would actually be in the outer domain. And by virtue of being in the outer domain but not in any world, we're representing B as a non-existent object. So note, of course, these worlds aren't disjoint sets, as they would seem to be here. As we just said, the same object A can exist in different worlds, and that's no different than in modal logic. Also note that non-existent objects are objects that don't exist in any world at all. An object that exists in world 1 but not in world 2 is still an existing object. So, as we just said less technically, in the Meinongian valuation, if A is a name, then the value of A is an element of the outer domain O. In other words, names may now refer to existing objects or non-existing objects. And this allows us to liberalize our condition on being the value of a proposition by removing the lined out condition from classical predicate logic. So in classical predicate logic, we have the condition that if P is a one-place predicate, for example, and A is a name, whose extension value A is an element of DW, then, so actually this is classical predicate modal logic, then the value of PA at W is true if and only if the value of A is an element of value of PW, etc. So by removing this lined out condition, we have a much simpler, even though it seems like we're talking about something more complicated, a much simpler condition. So now it just says if P is a one-place predicate and A is a name, then the value of PA at W is true if and only if the value of A is an element of the value of P at W. In other words, we just don't have the existence condition being a member of the domain of some world. So an important subtlety easily missed is this. When we state these valuation rules, which were just on the previous page, it might seem as if we're continuing to require that objects exist in some world, W, in order for us to ascribe properties to them, whether truly or falsely. But that is not what these expressions say. What they say is that propositions, whether they are about existing objects or non-existing objects, are always true or false in a particular world. So in other words, we do not speak meaningfully about the truth or falsity of a proposition except in the context of a particular world. This is true of modal logic generally, not just free modal logic. Moreover, what this also means is that when we specify a model in Meinongian free logic, we must specify the extension of the predicates for each world, not only for existing objects, but for non-existing objects as well. So to be sure we have a handle on this, let's recall how we do this for Leibnizian modal logic. So suppose we have three worlds, W1, 2, and 3, with three objects named A, B, and C, which all exist in at least one of these worlds. So recall that in Leibnizian modal logic, every named object has to exist in at least one world, and all worlds have to be populated by at least one object. There are no empty worlds. So recall that in classical modal logic, names denote existing objects only. So suppose there's just one-place predicate B for blue. Then to fully specify the model, again, remember, we're talking about Leibnizian modal logic, the modal logic that we're already familiar with. So to fully specify the model, we must specify the extension of this predicate, the value of blue for each world. So it might look like this. So the domain of world 1 is ABC, the domain of world 2 is AB, the domain of world 3 is BC. Obviously, this is much easier to see in a picture. This is how we have to do it if we're specifying it formally. And just suppose the value of B at world 1 is A. That means A is the only thing that's blue at world 1. And the value, say the value of B at world 3 is the empty set, and that's because nothing at world 3 is blue. There's something at world 3 that's required, but it's not blue. So in a Leibnizian model, it's fine if there are worlds such as W3 in which nothing is blue. But it would make no sense to say, for example, that the value of B at world 2 is AC, since at world 2, C does not exist, right? So we can't say that in Leibnizian modal logic. We can't say at world 2, C is blue. And how we just say, how could that be? C doesn't even exist at world 2. So that's what we're getting beyond in free logic. In free logic, it's actually going to be possible to say that at world 2, C is blue, even though it doesn't exist, which is what we say in English and what we want to capture in free logic. So the difference then between Meinongian and Leibnizian logic is that this is perfectly okay. Suppose, for example, that we add the name letter D, which refers to a non-existent object. This means that D belongs to the outer domain, but not to the inner domain of any particular world. Now, because truth and falsity is relative to objects in the outer domain, not the domain of a particular world, we can sensibly say, for example, that D is blue in world 1, even though D does not refer to an object that exists in world 1, or, in fact, in any world at all. So, for example, this is a perfectly sensible model with one extra world. And this sort of summarizes our situation nicely. So if you'll look at each of these categories, you'll see something we're able to do in Meinongian logic that we're not able to do in Leibnizian logic. So in this case, we see the value of blue at world 1 is the set containing A and D, even though D does not exist in world 1. So it's just the fact that in world 1, D is blue, even though D does not exist in world 1. And here we have the same thing. We have C is blue in world 2, even though C does not exist in world 2, though it does exist in world 1 and world 3. We have here we have that D is blue in world 3, even though no existing objects are blue. No existing objects are blue in world 3. So we have B and C in world 3. Neither of them are blue, but there is something that is blue that just doesn't happen to exist in world 3. And then finally, something we've already noted, since names no longer have to denote existing objects, we're now permitted to specify worlds with no objects at all, but in which non-existent objects still have properties. So it could be, as in this model, that the domain of world 4 is completely empty, but in this world, A, B, C, and D are all blue. So as a result of what turned out to be pretty simple changes to Leibnizian modal logic, the logic of the quantifiers is now really drastically altered. For example, as Nolte proves on page 291 of the text, this inference is no longer a valid one. You can't infer from f of a that there exists an x f of x, which means, we're not doing derivation right now, but as you'll be able to anticipate, we're not going to have existential introduction as a derivation rule, at least not in this form. We'll have a different form, but it will just be a bit more complicated. So this is because A may now refer to a non-existent object. So, right, A may be funny, but we can't conclude from that there exists something funny because we have no assurances that A is not just a fictional entity. So this too is no longer a necessary truth, and so we're getting rid of an embarrassment in predicate logic and modal logic that we'd like to get rid of. There exists an x such that x equals x. So this, as we noted above, is the predicate logic way of saying that something exists. It's a theorem in classical logic because the models and worlds are defined as containing at least one member. In free logic, however, it is only the outer domain that is defined as non-empty. In our valuation rules, we countenance inner domains, dw, which may be empty. All of the worlds might be empty. So these are excellent limitations in terms of what we intuitively consider to be valid inferences in English. In English, we would say that in order to be able to infer there exists an x f of x from f of a, you would need an additional premise. For example, this should be valid. There exists an x such that a equals x. In other words, a exists. A is f, therefore there exists an x such that f of x. This is in fact a valid inference in Meinongian logic, and in developing our derivation system, we will change the rule of existential introduction accordingly. All right, so that's the introduction to the semantics of Meinongian free logic. I'll be giving you homework over this episode and ultimately cutting a video to review that homework.